Good morning, everybody.
Good morning, sir.
Good morning, sir.
So, could you please switch on your video for a few seconds, everybody? Okay, Shamrat, Srija, Aniruddha. Okay. Mokshumi, Devangana, please switch on. Shoham. Shamrat.
Yes, sir.
Yeah, please switch on your. Oh, Shamrat, you are on two devices.
Yes, sir. Actually, আমি পিসি থেকে স্ক্রিনটা দেখছি, ওই জন্য আমার পিসিতে ক্যামেরা আর নেই, মাইক নেই, তাই।
Okay, fine. Okay, you can now turn off your videos. Okay, so we have 16 so far. So let us wait for 1 or 2 minutes if anyone else joins. I think 26 of you have opted for this paper, right? Although in the last class, 21 were present, I think. Okay, so let's begin. Let me share my screen. So I think this was up to where we have discussed in the last class, right? That is how we can have, total global coverage of radio signals using three such artificial objects in space which are separated from each other by 120 degrees in angle. But also, in the last class, we had talked about that, when we try to establish a radio communication link over a long distance, then certain portion of the link has to pass through the lower atmosphere. So, the properties of the lower atmosphere, they should also be, well known to us. Like, for example, we had mentioned that in the lower atmosphere, you have these different weather-related elements being generated, like rain, snow, storms, etc. And it is a common experience for all of us that, like in the case of the direct-to-home telecast systems, DTH, any DTH service provider. So as an user, we have this experience that whenever there is a very heavy rainfall, the signal gets disrupted. We do not receive the different channels on our TV sets. So that happens because of the fact that water vapor or water in the form of rain has attenuation or imposes attenuation on these radio signals, which causes, the signal level to drop below a certain threshold, below the level which your receiver, that is your small, box that we can set-top box, so to say, that we keep besides our TV. So that is your receiver. So there is a certain threshold below which it cannot receive the signal. That means if the signal intensity or signal strength falls below that certain level, then that receiver will not be able to receive the signal. So when that kind of a situation happens, you do not receive any signal. So this is an example of the fact that how the lower atmospheric parameters, they could also, influence, or they could also disturb a particular radio communication link. So with that, we need to understand that the physical state or the physical parameters of this atmosphere, that should be divided into different regions, and there should be different schemes of such division depending on the basis. So one of the first divisions that we will learn about is temperature. Then we will briefly talk about composition, because composition, they do have some kind of an effect, but that is marginal. So basically temperature, composition, but we will put the greatest amount of thrust or emphasis on the distribution of the atmosphere on the basis of ionization, because it is this ionized property of the atmosphere, as we had shown in this particular diagram, that if this dashed line represents the lower limit of the ionized atmosphere, then essentially there are some properties of this ionized region which causes reflection of the radio signal from a certain point, so that we could establish a radio communication link between a transmitter and the receiver, which are not in direct line of sight and which may be separated by thousands of kilometers. Okay, so keeping that in mind, like for example, a simple calculation is that, if we assume the radius of the earth is 6,400 kilometers, then a simple calculation tells us that the total circumference will be 2 pi into r. So it will be something like 2 into 3.14 into 6,400, which will be roughly like 40,000 kilometers. So this distance could very easily, as shown in the figure, this could be like 1/4 of that distance. Okay. This is just a very crude estimate I am making. So this could be like 8,000 to 10,000 kilometers between the transmitter and the receiver. So it is a property of this ionized atmosphere which causes the reflection of radio waves, and what is that specific property and how it functions, we will come to that later on. But the idea is that this ionized, this classification of the atmosphere on the basis of ionization density. That is one of the most important divisions of the atmosphere, which is essential for establishing a radio communication link. So, moving ahead, like when we want to discuss about temperature, this is actually, a very good representation from a very old book. That is why, the pages are a little bit yellowish, but still, it is worth studying this. So, as we can see that the conventional idea or the common man's line of thought is that if we try to understand the variation of the temperature as a function of height, then essentially the common idea is that as we go up in height, we are getting closer to the sun, so the temperature should increase. Okay, that is the common perception, common man's idea that how the variation of temperature should be as a function of height. But as we can see from actual measurements that there is some kind of a quasi-periodic nature. It is not strictly periodic, there is some amount of periodicity, but it is more like a quasi-periodic variation of the temperature as a function of height. There are two minima and one maxima. So, from the surface of the earth, we could see that the lowermost region of the atmosphere in terms of the temperature distribution is what is known as the troposphere. So, the temperature from the surface of the earth gradually decreases. If we assume a surface temperature of about 270 to 300 Kelvin, so from there it decreases to about 190 to 220 Kelvin, 190 typically at the equatorial region and 220 at the polar region, and the corresponding height is something like 7 kilometers at the poles and about 18 kilometers at the equator. So this height where we have the first minima of temperature going up in height from the surface of the earth, that minima height is known as the tropopause. Okay, so the lowermost region is the troposphere, and this particular height is known as the tropopause. From the tropopause, the temperature once again starts to increase, and until we reach a maxima of something like 270 to 290 Kelvin. So this is something, this temperature is almost similar to what we have on the surface of the earth. This layer is known as the stratosphere. Okay, and this height where we have this maxima, that is known as the stratopause. Okay, the stratopause, and that typically occurs at heights of about 50 plus minus 5 kilometers. That means it could be from 45 to 55 kilometers. Then again, the temperature starts to fall. Okay, and we have a second minima occurring around 80 to 90 kilometers. Okay, and the second minimum temperature is a little less. I mean, it varies from about 150 to 220 Kelvin, and this height is this minima height is referred to as mesopause, and the layer between the stratopause and the mesopause or above stratosphere is known as mesosphere. And above this mesopause, the temperature increases almost exponentially with height, that is known as the thermosphere, and could very quickly reach values of 1500 to 2000 Kelvin. In fact, for the artificial satellites, they are mostly located at heights around or above 500 to 600 kilometers, most of them. Okay, even the nano satellites or the tube satellites that are gradually becoming popular nowadays. So they are also located at least at few hundreds of kilometers. So most of these artificial objects are subject to such high values of temperature, and that is a challenge for the designers of these satellite systems, because they have to give adequate, thermal protection or thermal shield for these artificial objects in space, because 1500 to 2000 Kelvin is a very high temperature, and one could simply try to understand or try to grasp the factor that when you launch these kind of artificial objects in space, prior to that you have to actually test it on the surface of the Earth in some laboratory by simulating these conditions. So just imagine that in a laboratory you have to simulate temperatures of 1500 to 2000 Kelvin and put your object there within that kind of an enclosure or maybe some chamber, and there the outside surface of the artificial object is fine, but within that you have to have the electronic circuitry. So those electronic circuitry also has to be of very special space qualified category. Anyway, coming back to this very interesting variation of temperature as a function of height, naturally the question comes to the mind that when we have this kind of a variability of the temperature, there must be some heat loss processes occurring near the minima and some sources of heat which are present around these regions of maximum. Okay, so the heat sources like near the ground over here, they are simply the radiation from the, or I should say re-radiation from Earth's surface. That means the solar radiation falls on the surface of the Earth and heats up, and then the Earth also re-radiates some part of that incoming radiation. So that, we will be dealing with all these issues in a very simplistic way without going too much into the details, because that is not the focus of this particular paper. Then near the peak around 50 km, that means at the stratopause height, you have secondary maxima of temperature happening of 270 to 290 Kelvin typically. These are typical values. So that is actually caused by the absorption by ozone of the solar UV radiation. That means around these heights we have the ozone concentration, major part of the ozone concentration, and that absorbs the solar UV radiation, but within a certain wavelength range of like 1650 to 2500 angstrom. Within that range, the incoming solar UV radiation that is absorbed by the ozone, which is predominant at these altitudes of around 50 km above the surface of the Earth. And then in the thermosphere, essentially the dissociation and the ionization of these atmospheric gases which are there above 100 km, they happen by the solar UV radiation, whose wavelength is within say 1750 angstrom. Okay, the sun is a source of radiation in different wavelength bands, and depending on which wavelength band you are looking at, there could be interaction with the atmospheric gases in different wavelength bands. মানে বিভিন্ন atmospheric gas বা বিভিন্ন atmospheric constituent তারা কিন্তু এই সোলার ইউভি রেডিয়েশনের বিভিন্ন ওয়েভলেন্থের সঙ্গে তারা ইন্টারঅ্যাক্ট করে some of them absorb the solar UV radiation, some of them gets dissociated and ionized like that. And the heat loss processes up to about the first 100 kilometers, like up to almost like the thermosphere, that is essentially the heat loss process is the infrared radiation. মানে এই যে ইনফ্রারেড রেডিয়েশন বলতে সিম্পল বোঝায় যে আমরা ধরো আজকে একটা কোনো মেটালিক অবজেক্টকে গরম করলাম, করে সেখান থেকে যে হিটটা আমরা এক্সপেরিয়েন্স করি when we bring ourselves near to that, when we bring our hand near to that, that is one example of infrared radiation which could happen to, which could damage us and which could also happen to different kinds of, atmospheric constituents. So the heat loss process within about up to about 100 kilometers, that is mainly caused by the heat transport by convection. So above 100 kilometers, it is the conduction downward. So towards the surface of the earth, that means towards the mesopause. So these are basically the two primary heat loss processes which takes place. So the idea is that once we know the variability of this temperature as a function of height, so that will also help us in understanding that how the radio signals may be affected when it traverses through these regions of the atmosphere. So, as I was saying that in the troposphere, the temperature decreases with height up to the tropopause, and its average altitude, it varies from about 18 kilometers at the equator to about 7 kilometers at the geographic poles. And there is a term known as the lax rate in the tropopause. The lax rate. Lax rate means essentially the rate of change of temperature or drop of temperature with height. So in the lowest region, that means from the surface of the earth to the tropopause, that lax rate is something like about -6 Kelvin per kilometer. The minus sign because the temperature is decreasing. So for every kilometer it decreases by roughly about 6 Kelvin, and that leads us to a tropopause temperature of about 200 Kelvin, as we have mentioned over here roughly. Then in the stratosphere, once again the temperature increases to about 270 Kelvin, and above that it falls again in the middle atmosphere or mesosphere. Now one of the questions which should immediately come to our mind is that how are these temperatures measured at these altitudes, like 50 kilometers or 100 kilometers above the surface of the earth? It is not possible for humans to fly in a balloon and with a thermometer in their hand and make the measurements at say 50 kilometers or 100 kilometers. Okay, 50 বা 100 kilometers মানে কিন্তু অনেকটা altitude. Okay, normally all the airplanes, they fly within the first say 8 to 10 or maximum 12 kilometers. Okay, মানে পুরোটাই হচ্ছে তারা ফ্লাই করে within the troposphere. এই stratosphere, mesosphere এই সমস্ত তো তাদের মানে এয়ারপ্লেনে যাওয়ার কোনো অবস্থাই নেই. Okay, so that is why it is a natural question which should come to our mind, that how are these temperatures measured at these altitudes. So there have been several rockets. Rocket money into, don't confuse that with the satellite launches that we normally see. Okay, we see the huge object, a huge rocket-like thing carrying an object, and with increase in altitude, one stage falls off, the second stage carries on, and so on. It is not like that. By this, these kind of rockets are much smaller, and they are able to reach altitudes of about say 50 to 100 kilometers typically. Okay, usually up to 70 to 80. 100 kilometers is a bit too high for these rockets, and they have some kind of a thermal sensor on board, and these thermal sensors, while going up, while the rocket goes up or moves up, they send back the data through some kind of a wireless network. Okay, in the earlier days, what happened was that they used to, when the rocket used to go up, then at the topmost height, it usually used to get defragmented, মানে সেটা একেবারে ভেঙে যেত, এবং at that time, that some kind of a thermal sensor with the data stored in it, that used to fall down, and there was some kind of a small parachute which would automatically open up, and that thermal sensor with the data could land at some place. But nowadays, with the advancement of technology, we have this kind of rockets available which goes up and then they kind of send the data downwards to the ground station using some kind of a wireless link. So that is very roughly speaking, very simple. I am saying this in a much simple way. There are actually several different complications involved in this measurement as well. But this is roughly the principle which is followed in making these measurements. Now, if we look at this figure, then we could also see that there is another classification mentioned, that there is some kind of a homosphere and also a heterosphere with a boundary occurring around 105 to 110 kilometers. So this classification is on the basis of the composition, and that boundary layer is referred to as the turbopause. Okay, that means if you wish to classify the atmosphere on the basis of composition, then you have these two layers, heterosphere and homosphere, and there are several different atmospheric chemistry processes which takes place. That what are the causes of heterogeneity in the upper atmosphere, I mean above 100 or 110 kilometer, but below 100 kilometer it is essentially more like a homogeneous mixture. So that is why that causes this kind of a classification into the homosphere and the heterosphere. Now, this is actually some kind of a height variation of the neutral particle density. So this was derived when I wrote down these derivations, and then I scanned it and put it here. I realized that the letters were, I think, smaller than you could possibly see. Is it possible for you to see this? Can you see this?
Sir, if, while seeing on the laptop, you can see it if it is in full screen mode, but it is a bit difficult.
Yeah, I mean, I'm in the full screen mode, so that's why, I once again wrote it down yesterday. I think this is something which you can see better, right?
Yes, sir.
That is, the basic idea is we try to understand that so far, whether you are dealing with the temperature variation with respect to the temperature, the atmospheric division with respect to temperature or composition. Now, other than these two, there is also some kind of a classification which is based on ionization, on which we should actually put more stress, because this particular property of the atmosphere actually causes or helps the reflection of radio signals and establish long distance communication. মানে আয়োনাইজড অ্যাটমসফিয়ারের এই প্রপার্টিটা না থাকলে কিন্তু লং ডিসটেন্স কমিউনিকেশন আমাদের পৃথিবীতে সম্ভব হতো না। That is the bottom line. So that is why we need to put more stress on this particular classification or classifying parameter, that is ionization. So when we speak about the ionized part of the atmosphere, we should also understand that there is also a neutral part which is electrically neutral. Okay, by neutral I mean they are electrically neutral. So in the neutral atmosphere, what kind of physics is there, and how the neutral particle densities they vary as a function of height, that should also be known to us. Because once again, if I repeat, then the signal also has to propagate a certain distance through the neutral atmosphere before it is incident on the ionized part of the atmosphere. So basically we begin with the fact that the variation of pressure that could be expressed as, that means an infinitesimal change in pressure is related to height through this relation rho g dh with a minus sign. The minus sign indicates that as we go up in height, pressure falls. And then this rho could also be expressed as, the product of mass of a particle times the particle density. Okay, so this g is the acceleration due to gravity that you know of. Then again, from this perfect gas law, we know that P is n into kT. Okay, K is Boltzmann's constant. So basically, this dP by P, if we take the ratio, then that will be simply, I put this minus g mn dH by nkt. This n and that n in the numerator and denominator, they cancel out, and we get this minus dH by kT by mg. That means I am bringing this mg down to the denominator. So I express this pressure, infinitesimal change in pressure by the pressure, that ratio, as minus of this infinitesimal change in the height by a factor capital H, where capital H is equal to kT by mg. This is the scale height. Okay. So this is a particular parameter which is the product of the Boltzmann constant times the temperature by the mass of that particular atmospheric constituent into G. Okay, so that means this scale height will actually be different for different atmospheric constituent. So from this relation 2, if we do this simple mathematical step, that is we do dP upon P, so that will be dN by N plus K is a constant, so the differential of that will be 0 plus dt by T. Now, if we make kind of simplistic assumption that we have an isothermal atmosphere. Just now we have seen that the atmosphere is not isothermal. We have seen the variation of the temperature as a function of height. So definitely it's not isothermal. But for the purpose of simplifying the calculation, if we just assume for the time being that this is an isothermal atmosphere, then effectively the T will be a constant. So this dt, that will be equal to 0. So you will have this dP upon P equal to dN by N. Okay. And so this dN by N, because dP by P we have seen from here is minus of this dH upon capital H. So this will be dN by N will be minus of dH by capital H. So now if we integrate and put the boundary conditions like n equals to n naught at h equal to 0, that means at a reference site h equal to 0, the value of this particle density is n naught. Then you arrive at this kind of a relation that n, the neutral particle density, is n naught e to the power minus small h by capital H. Now, if we so far, you see that means there is, when we consider the variation with height of the neutral particle density, we see that it exponentially decreases as a function of height. That is why the lower part of the atmosphere is sometimes also referred to as an exponential atmosphere. Okay, exponential atmosphere. So this is an important relation because this will actually, kind of guide us when we try to derive the variation with height or other parameter of the ionized atmosphere. This is for the neutral atmosphere, electrically neutral atmosphere. So when we go into the ionized atmosphere, there also we will see that this particular relation n equals to n naught e to the power minus small h by capital H, that also has got some relevance over there. So far, we have considered this scale height as simply, kind of mathematical factor. But আমরা kT upon mg বলেছি without trying to understand that what is the physical meaning of this kind of a height, or এটাকে height কেন বলা হচ্ছে, because in this relation now, if we put small h equals to capital H, then we arrive at this relation that n becomes equal to n naught e to the power minus 1. এখানে কিন্তু একটা জিনিস মাথায় রাখবে, অনেক সময় স্টুডেন্টরা ডিউরিং দ্য ক্যালকুলেশন এন্ড ম্যাথমেটিক্যাল প্রবলেমস করার সময় দে টেন্ড টু কনফিউজ দিস e with the electron charge. It is not. This is the e for the exponential. So, 1 by exponential is typically, if you put the value, it will be like 1/3. Okay. তার মানে the scale height is that height where the neutral particle density becomes 1/3 of that at the reference height. That reference height could be at the surface of the earth also. তার মানে এতক্ষণ পর্যন্ত we have expressed the scale height only as some kind of a mathematical parameter, but now we have some kind of an understanding that it is that height at which this neutral particle density becomes 1/3 of that at the reference height. Okay. Then again, another important conclusion that we can derive from this particular relation, exponential relation, is that if we integrate this from a reference height h to infinity, say for example, then it means that we are putting this value n naught e to the power minus small h by capital H dh. So, তোমরা কেউ একজন জাস্ট এইটাকে একটু সবাই এই ইন্টিগ্রেশন লিমিটস গুলোকে একটু পুট করে দেখো তো whether you are arriving at this kind of a relation or not. You get my point?
Yes, sir.
That means just the limits of integration and check.
Yes, sir. We will go to that point because one limit will lead to 0 and the other will be h.
Have you done this?
Sir, I did it right now.
Okay. So could you just show me the page now?
Sir, it is a bit difficult because I'm on my laptop and I need to scan it then.
No, you don't have to scan. Just hold it in front of your screen. That will be all.
And okay, sir, I'm trying to show, but
Just hold it in front of the screen. That will be fine.
okay, sir. Just a minute.
Just turn on your camera and hold it in front.
Yes, sir. Yes, sir. I'm showing it.
Yes, Chirantam.
Yes, sir. Sir, okay. Is it possible to see? I don't know. So one limit of infinity will lead to 0,
Yes.
and then there is this power of minus h by h. So that multiplication of h will happen due to as we are integrating.
Okay, let us see. আর কেউ একটু করো তো এই ইন্টিগ্রেশনটা।
And there will be one by e term coming out. So n not by e will happen.
Okay, let us see what the others have to say. Okay, thank you.
Okay.
বাকিরা একটু আমাকে বলো তো ইন্টিগ্রেশনটা করে লিমিটসটা বসিয়ে ইন্টিগ্রাল ফ্রম h টু ইনফিনিটি n dh।
স্যার করেছি। স্ক্রিন প্রেজেন্ট করব?
দেখাও দেখি। হ্যাঁ দেখাও। ওকে ওকে ওকে, ঠিক আছে, ফাইন, আমরা দেখতে পাচ্ছি। ওকে, বাকিরা কি করছে দেখি। মৌসুমী মণ্ডল, থ্যাংক ইউ। মৌসুমী মণ্ডল,
Yes, sir.
তো তুমি একটু আমাকে করে দেখাও স্ক্রিনে।
Sir, a minute. স্যার করেছি।
একটু স্ক্রিনে দেখাও। Okay. Okay, so this was Shamona Majumdar, not Moshumi Mondal, right?
Yes, sir.
Okay.
Sir, I have done it too.
Yeah, Shavni.
Sir, 1 minute.
Yes, Shavni.
Yes, sir, I'm streaming. Is it visible?
Yeah.
Sir, this is the integration. So first I integrate it in this way, that is, this is the variable e to the power minus h by h, because n0 is constant. So it will go out, and then we'll integrate, and we'll get this e minus h by minus 1 by h. So on simplification, we get minus n0h e to the power minus h by h from limits small h to infinity. On integrating, on putting the limits, we get minus n0 h e to the power minus infinity, that evaluates to 0, and this is the remaining part, n0 h e to the power minus h by h, and n0 e to the power minus h by h is again n, so this is what we get.
Okay, thank you. So, what we can understand.
Hello?
Okay. You please stop presenting. I will go back to my presentation. Yeah.
Sir, can you hear me, sir?
Yes.
Hello?
Moushumi? Yes.
Sir, actually, I did the same process, but that the limit, can I show it, sir?
It is from H
Hello?
to infinity.
So the limit is h from infinity. So when I the last limit, when I putting the value minus h small h by small h, that is e to the power minus 1. So can I just put the value 0.036?
You want to put the value where?
E to the power minus small h by small h, so that is e to the power minus 1.
Yes.
So I was just putting the value, that is e to the power minus 1, it is 0.36. So it's become 0.36 capital H into N naught.
No. Eventually, if you arrive at this kind of a relation, that is, you have this n naught, the reference value of the particle density, and then this exponential variation and this capital H, then you will eventually arrive at this one. If there are any confusion, then I think I will once again put these limits and actually do this and show you in the next class. Okay, but I don't think that will be there will be any problem with it. I mean, because some of your friends have already done that. The basic idea that I want to convey is that it means that if you integrate, I mean, this is so far just a mathematical operation that we have shown. The physical interpretation of this is that if you integrate this neutral particle density from a reference height to infinity, basically to infinity means to large heights above the atmosphere, to the top of the atmosphere, say, then you arrive at a value which is equal to the product of the particle density at that height, at the higher height, times the scale height of that particular product, of that particular constituent. That means you need not have to make the measurement of this, total columnar concentration. That means assuming that it is some kind of a column which is imaginary column which is extending right through the atmosphere, and you want to integrate the particle density which is present within that particular column, you do not have to do that at each and every height within that column. What you need to do is at the topmost height, which is the upper limit of your integration, you make the measurement of this neutral particle density and then you simply multiply that by the scale height. Because if you know the, say for example, the molecular weight or the molecular mass of that particular constituent, then this K and T and G, these are known to you, so you can very easily calculate the value of the scale height. So simply multiply that scale height with that single measurement which you make. That single measurement for all practical purposes will be, say for example, if you want to integrate up to say 100 kilometers or 50 kilometers, whatever. So that single measurement has to be made at that height only. So that is the basic principle of the advantage of having this kind of a relation. That is, instead of making a measurement at each and every single point within that particular height range, you make a single measurement at the topmost height and then you simply multiply that by the scale height of that particular constituent, neutral constituent, in order to get the total contribution due to that particular species. Now, moving ahead, this is one particular table, which should be of, which you should keep at your fingertips. Okay, in this entire ECE course. That means for the purpose of different kinds of applications, what are the radio frequency bands that are used, and what are their names, what are their ranges, and what are their conventional single letter representation. Okay, like when somebody says later on, maybe in some of the next semesters, maybe the teachers will be saying only that try to design a HF communication link or a VHF communication link. They won't be telling you about what is the frequency range or things like that. So when you say HF, automatically you have to understand that it is this particular range of frequency that is being talked about. VHF is this particular range. And then these are less frequently used, like super high frequency or extremely high frequency ranges. Then millimeter waves, that means anything which is above 300 gigahertz, that is known as millimeter waves. And within that millimeter wave, once again, you have, within the microwave range of frequencies, once again, microwave is anything about 1 gigahertz. Okay, so within that microwave range, once again, you have different kinds of nomenclature. Okay, there are two conventions. This is the old convention, but this is more commonly used even today. This is a new convention. It is less frequently used. Like the 1 to 2 gigahertz band is referred to as the L. Then you have 2 to 4 gigahertz, the S band. Then from 4 to 8, you have the C band. 8 to 12 is the X band. 12 to 18 is the KU band. 18 to 27 is the K band. And 27 to 40 is the KA band. And above 40 gigahertz, you have this millimeter waves. Okay. So this is something which should be at our fingertips in all the subsequent semesters. Okay, so I think I will stop here because that classification of the atmosphere according to the ionization, that we have very little time left today. So I will start it in the next class. So let me have your attendance now. Okay, so this is intake. Intake. It's 13. Okay. Shubhadeep Mukherjee.
Present, sir.
Moshumi Shah.
Present, sir.
Srija Chakraborty.
Present, sir.
Samora Majumdar.
Present, sir.
Moshumi Mondol.
Yes, sir.
Shamrat Malakar.
Present, sir.
Debraj Dash. Okay. Shomodip Bashar.
Present, sir.
Devangana Bashar.
স্যার ও ক্লাসে
she was-
ছিল, ও চ্যাট বক্স লিখেছে, ওর ওয়াইফাইটা ডিসকানেক্ট হয়ে গেছে।
Oh. Arup Kumar Marik.
Yes, sir.
Shayani Roy.
প্রেজেন্ট স্যার।
Soham Paul.
Present, sir.
Shagni Nayak.
Present, sir.
Chiranthan Ganguly.
Present, sir.
Aniruddha Mondol.
Present, sir.
Amitrakshar Sanya. ও কি এই কোর্সে আছে অমিত্রাক্ষর সান্যাল নাকি?
হ্যাঁ স্যার আছে।
Okay. Pothikrit Gupta.
Yes, sir.
Shreyashri Rai.
Present, sir.
Ritik Majumdar. Suprabhat Bhattacharya. Shayan Datta.
Present, sir.
Okay. Okay, so thank you. And we meet again in the next class, next Tuesday. Thank you.
Thank you, sir.